Good evening, everyone. I, Professor Kachal Paviskar, welcome you all again for the second day of our webinar. So after yesterday's wonderful session on UV spectrometry, today Sir is going to explain about another very crucial topic, that is spectrophlorimetry. I'm sure students, you will learn a lot today. So without much ado, I would like to invite our resource person, Dr. Krishnamurthy Bhatt. Please, sir.
Okay, now can I share my presentation?
Yes,
sir.
Yes,
Hello.
visible.
So I can show my screen.
Yes, sir.
Yes, sir. Yes, sir.
Is it fine? Is it
Yes,
fine
sir.
now?
Your screen is now visible.
PPT is visible now?
Yes, sir.
Yes, sir.
Hello.
Yes,
Okay.
sir. It is.
So I can start.
Yes,
Sir.
sir.
I'll start. Okay. Good evening, everybody. Now, yesterday we have discussed about UV visible spectrophotometry, and today we continuing with that discussion. We will go see spectrophlorimetry. Now, yesterday we have seen that spectrophotometry or UV visible spectrophotometry, whatever we call it, is essentially an absorption spectroscopy. That means we build a relationship between the intensity of absorbed radiation with concentration for quantitative purposes, and the wavelength of absorbed radiation with the molecule for qualitative purposes. That is essentially a qualitative, absorption spectrum. The fluorescence is, or fluorimetry as analytical technique is different from UV in that aspect, that here we don't look at the intensity of absorbed radiation, but we look at the intensity of emitted radiation. Now, what is this radiation is all about, what we are talking. So this is what is called electromagnetic radiation. When we say radiation, what we mean is electromagnetic radiation. Now, this electromagnetic radiation is a huge band of radiations, as we have seen yesterday, wave form, generally wave, and that will have the electrical and the magnetic component, and it's a huge spectrum. At one end of the spectrum, we have radio waves with the wavelength of 10 to the power of 3 meters, that is merely 1 kilometer. On the other side of the spectrum, we have gamma radiation, which is 10 to the power of minus 13 meters. Now, in between, we have a lot of useful radiations from analytical perspective, and they are microwave, IR, and UV, visible, and then X-rays, things like this. Now, every part of this EMR would deal with some analytical technique. As we have discussed, the energy of the radiation decreases as the wavelength increases, and vice versa. So these radiations will have very high energy, and these radiations will have low energy. Radio waves and microwaves will have very low energy compared to gamma radiation, which will have high energy. Amongst this also, IR will have lesser energy than UV, and X-ray will have more energy than UV, and things like this. Now, today's topic, we will be talking about this region, that is around 10 to the power of minus 3 to minus 9 meter. wavelength range, that is UV and visible. Fortunately for us, both both UV and visible essentially work in absorption in the UV visible spectrophotometry and fluorimetry works in UV visible range, and that is why both of them are generally combined. But the difference is here what is measured is emission intensity, not the absorption intensity. So as I have told you, this is what is in words the phenomenon of emission of radiation when the molecules are excited by radiation at certain wavelength, and this measurement is called as fluorimetry. Now, as we have seen yesterday, the compounds containing sigma, pi, and n electrons would be excited, and they will be excited to HOMO, and then they'll come back to LUMO. And now, when yesterday we have been talking about the excitation and spending of energy, and that is what we are measuring. Now, as the law of conservation of energy says, any energy which is absorbed has to be emitted, and as a law of nature, nothing at excited state is stable. Anything in nature is least or most stable at least energy state. That means any molecule or atom or ion is most stable at its ground state. Now, when it is excited, it eventually has to come down to ground floor, and when that happens, when it comes down to ground floor, the additional energy which it had is emitted in this form. We will come to this diagram a little later. When the electrons are promoted before emitting radiation, what happens is there can be three states. One is singlet state. Singlet state is when all the molecules in the, all the electrons in the orbit are paired, whereas doublet state is one where we have one unpaired electron, and then triplet is two unpaired electrons. And in excited states, generally they are unpaired with opposite spin. That means something like this. Okay. Now, once the absorption happens, the elimination or emission of radiation will happen. Emission of radiation can happen in, or reduction in the energy of those excited electrons can happen in three methods. One is collisional deactivation, another one is fluorescence, and the third one is phosphorescence. Amongst these three, we will be specifically talking about fluorescence in today's class. Now, how is this? What is the difference between these three, collisional deactivation and fluorescence and phosphorescence? This diagram explains that. Okay. Now, this is what is excitation, blue, the green lines, and the red lines are the fluorescence emission. Right. This is what is fluorescence emission, which is the central theme of our discussion today. But this is what is the radiation-less emission, what we are talking about, where the energy content is reduced, but no detectable radiations are emitted. And it may also slowly lose the energy in what is called as intersystem crossing, right? That is essentially a non-radioactive relaxation. So if there is no radiation as given, then we cannot measure. When we cannot measure that, obviously we cannot quantify, we cannot do anything with that measurement. Right? Now, coming to the next part. Yeah, these are the types of emission which can happen. Collisional deactivation, and the fluorescence, which we are going to talk, and phosphorescence, which I have just explained with the help of that diagram. Same thing is written in words here. Fluorescence. Now, you may ask why? How do we determine which process happens in what conditions? Now, that depends on the structure of the compound. Now, simple organic compounds, which are low pi star energy transition stuff, does not show any emission. The relaxation happens either through intersystem crossing or collisional deactivation. Even if it absorbs radiation, like as we have seen yesterday, these compounds will absorb some radiation, but no fluorescence, like pyridine, pyrrole, etc., will absorb some radiation because they have conjugated systems, but they don't emit radiation in fluorescence, or they are useless as far as fluorescence analysis is concerned. But when these molecules are fused with benzene ring, then those compounds show the fluorescence, like quinoline, isoquinoline, indole, etc., have very great fluorescence capacity. Now, there is also another reason with the specific intensity of emitted radiation, that is about the rigidity of the structure. Now, if you can see these two molecules, fluorine and biphenyl, fluorine is by far the more rigid than biphenyl. Biphenyl has a flexible structure here, flexible bond here, whereas this is a ring structure. So fluorine would give high intensity emitted radiation or high intensity fluorescence than biphenyl. That's essentially because of the rigidity of the molecule. Same thing is with 8-hydroxyquinoline and the zinc complex of zinc 8-hydroxyquinoline. This is a huge rigid structure. The complex you can see, right? Zinc and two molecules of 8-hydroxyquinoline, and that is why the intensity of this complex is much higher than the simple standalone 8-hydroxyquinoline structure. Now, coming to the other factors which are influencing the fluorescence intensity, structure, we have seen rigid structures, and then we did the bonds, conjugated bonds, and anything other than sigma to pi or sigma to sigma star transitions, which will give better fluorescence. The concentration, quantum yield, intensity of the incident radiation, adsorption, oxygen, pH, temperature, viscosity, photo decomposition, quenching, and scattering are the other factors which would affect the intensity of fluorescence. Now, how the concentration would affect? Fluorescence follows exactly same equation as that of Beers-Lambert equation in absorption spectroscopy. That is, A is equal to ABC, where this A, the capital A, is the intensity of emitted radiation, and this is the emissivity, path length, and concentration. So that means higher the concentration, because they are directly related, higher the concentration, higher will be the emission intensity, and vice versa. And so concentration effect, and this is what is used for all quantification in fluorimeter. Now, other factor which affects the intensity of fluorescence is quantum yield. So what is quantum yield? Quantum yield is nothing but the ratio of number of photons emitted to that of number of photons absorbed. That means it is very similar to the intensity of radiation, but it is number of photons what we are talking about. We have seen I0 upon I in case of absorption spectroscopy. So same way, this is the number of photons. Now, please remember, quantum yield can never be more than 1. 1 is the best number possible with quantum yield, basically because that will give the 100% emission from the incident radiation. Okay, now higher, but nevertheless, higher the quantum yield, better or more sensitive the method is, or the analyte is for for analyzing by fluorimetry. Now, intensity of incident radiation, of course, once you know this formula for quantum yield, higher the intensity, higher will be the photons here. So for a given quantum yield, if the photons absorbed are more, photons given out are more, so that means the more intense emitted radiation is observed. If the intensity of excitation source, or the light source, incident radiation is high. Now, oxygen can sometimes create problems because of oxidation, especially at high energy stage like excitation. It may oxidize the species to a leucobase, that is a non-fluorescent compound, thus giving or reducing or stopping the intensity of emitted radiation. pH, as we have seen in differential analysis in case of UV, pH can also change the structures and the conjugation of the compound. Hence, in certain molecules, pH can change or can alter the intensity of radiation. Temperature and viscosity also play a major role in the absolute intensity of emitted radiation. Higher the temperature, lower the fluorescent intensity, essentially because of the collisional deactivation. Because if the temperature is increased, the kinetic energy of the system is more, and that is where the molecules would start interacting with each other. They start moving faster because of the kinetic energy. They start interacting, and that is where the intensity the emitted radiation is lost partly. That's why the intensity of the fluorescence is reduced at elevated temperature. Now, if the viscosity of the solution is high, then the collisions are reduced because the molecules have to travel against the viscosity. Viscosity will give a very thick medium, and that is why, whereas light is not affected by viscous solutions. So that is why higher amount of emitted radiation is detected. So the fluorescence intensity increases and viscous solutions than the non-viscous solutions. Now, these things are can be taken care. Sometimes, we may have or high viscosity or high temperature solutions are inevitable. When we are doing quantitative estimation, we really need not have to very seriously bother about it, as long as it meets our other requirements, because the standard and the reference and the blank should have the same temperature and viscosity conditions. If we use a blank of different viscosity and the sample of different viscosity, or the reference solution of different viscosity, then we are inviting trouble. But otherwise, if you don't want any troubles in quantitative analysis, keep the viscosity and temperature of all solutions at the same value, so that there is no effect of those variables on the final result of analysis. Now, how can we do it? Now, we are talking about blank, especially blank. Yesterday we were talking about using blank, reagent blank and solution blank. So if the viscosity is, if the reagents, if the solution, the sample is not prepared in water, then preferably go for the same chemicals and same system, except the analyte for preparing the blank. That means if you are derivatizing the analyte to get fluorescence, add all those chemicals in the same proportion to that of the blank as well, except for the analyte, so that we don't encounter changes in viscosity or temperature of the blank. That is what is called as reagent blank. Reagent blank will have everything as that of the sample, except the sample analyte or the sample of the analyte itself. Whereas solvent blank is nothing more. Only solvent which is used to prepare the analyte solution is used. Now, photochemical degradation, because very high intense radiation falls on the sample solution in liquid state. Any chemical is more active in liquid state. So apart from that, if you bombard that with high energy visible or UV radiation, there are chances that that it induces some photochemical degradation or photochemical reaction, which we need to be careful when we are going for fluorescence. Now, what is this quenching? Quenching is essentially reduction in the fluorescence intensity because of various reasons. Quenching can be classified into four. One is inner fluorescent effect, that is essentially the parts of the instruments which are responsible, which absorb some radiation and then give you less intensity of fluorescence. Self-quenching is the one where the analyte molecules themselves absorb the emitted radiation, and that is where the intensity is reduced. Now, how do we understand this? Now, imagine a solution has 100 molecules and there is another solution which have 1000 molecules. Now, one with 100 molecules is in a given volume, say in per ml. Now, per ml 100 molecules, they are distributed uniformly across the medium. So the emitted radiation, they don't come on the way of emitted radiation. Emitted radiation can directly reach the filter and subsequently the detector. Whereas if there are 1000 molecules in the same 1 ml, now it is something like a crowded marketplace. The same analogy what we are talking now in case of COVID, we say social distancing. Why the cinema halls are not open during this COVID time, or the public functions are not held during this time, or even the government of Maharashtra has not permitted any Ganesha festival to be occurring for the same reason. There will be a lot of people, so crowding, the distance between individuals would be less, so the virus emitted by one person can enter into the system of other person. Now, same way, replace those individuals with the molecules and virus with radiation, you understand what is self-quenching or concentration quenching. Right now, collision quenching is also called as chemical quenching. There are some chemicals, halides, which are most commonly known chemical quenchers. So there, the chemicals, halides, or those things go and interact, or they absorb the radiation, emitted radiation, and that is where concentrate, but the intensity of emitted radiation comes down. And static quenching is essentially because of the chemical reaction between maybe the analyte or the excipients in the sample and that of the the emitted radiation. The complex formation between analyte and some excipients or unwanted compounds, or maybe the other analyte, which that's also possible. So scattering is essentially the Tyndall effect, and all of we have studied in physical pharmacy. Scattering is essentially because of non-homogeneous solution. If it is homogeneous solution, scattering by and large is not a problem, unless otherwise the molecules, the solute molecules are very large. If the molecules are large, and then some sort of Raman scattering can happen, but that is not a very general case. That's very specific cases, right? Now, coming to instrumentation, a typical fluorimeter would look something like this, right? You have a source and we have a collimator. Collimator is the one which makes this molecule, this radiation in parallel, and then we have the slit through which the radiation passes, and then there is monochromator. There are actually two monochromators, and this is monochromator 1, and then there is sample. So the radiation which is coming will pass through the monochromator and impinge on the sample. So the radiation, the light is emitted, the unabsorbed radiation passes straight, and that is why we don't keep the detectors at straight line to the light source in fluory. We always keep it at 90 degrees, because Here are the transmitted radiation, right? This transmitted radiation goes straight. So what we want is emitted radiation. Now emitted radiation, this is where it comes from, and it again passes through the other monochromator and then the detector, right? Once it falls on the detector, amplified, and then it goes to the record. Now, what are the different light sources which are used in case of this thing? In case of fluorimeter, the first one, the most commonly used is mercury vapor lamp. That means mercury and high pressure is converted into vapor inside this lamp. This is how a typical mercury vapor lamp will look, and this you can see is glowing. And then at high pressure, when you apply the power, when you pass the electricity at low pressure, mercury vapor, it starts emitting radiation. Generally it emits at 350 nanometers, and then it also emits at 254 nanometer. So if you are working at 254, then probably you don't even need a monochromator. Here you can straight use mercury vapor lamp and construct an instrument. Now xenon arc lamp is most widely used because it gives very high intense radiation, and this is how it works. And these are the arcs. You know, it is not a spark lamp, it's an arc lamp. And then this here is the xenon, and then we have an anode and a cathode. And when there is an arc which is produced, and that arc, you know, you can see here, gives a very intense radiation, but that is polychromatic radiation. And this is a quartz envelope through which the UV radiation will pass, and it gives very high intense radiation, and very useful, largely used in most of these fluorimeter. The other one which we can also use is the tungsten filament lamp, which is nothing but the same light bulbs which we use at our home. All of you might have heard Gola, right? The old time, some of us also might have seen in villages and, you know, other places. Nowadays of course it's not very widely used, but then, you know, once upon a time, maybe 10-15 years earlier, it was very common source of domestic lighting, what in Hindi called as Gola, right? This Gola is same, nothing but the tungsten filament lamp. This is the tungsten filament, and here is the electrical system, and then the power supply, and the incandescent lamp. It's also called as incandescent lamp because this tungsten filament incandesces at high temperature because of the power, and then, you know, it gives the intense radiation, right? But it gives only 15% of its radiation in visible range, another 85% in IR range. Now after that, what we have next is filters and monochromators. Filters, any color filters can be used, which are same as that in UV visible spectrophotometers, that is the colored solutions, or the glass filters, or gratings. Anything can be used, but spectrophotometer, as I have showed you earlier, will have two filters, one as excitation filter and the other one is emission. Now excitation filter is to convert the polychromatic excited radiation into monochromatic excitation radiation, and the emission filter is to convert the polychromatic emitted radiation into monochromatic emitted radiation before passing into the detector. Okay, depending on the make of the instrument, it can be filter or monochromatic. Gratings are also used, especially in spectrophotometer. We use gratings, not the filters. The sample cells can be a rectangular, you know, typical UV, typical UV visible spectrophotometer type to it, but it can also use the cylindrical, sample holders. Here is what is the sample is filled, and then measured. We can also have small volume cuvette for holding the sample with small gap here, so that small volumes can be measured. But of course that's possible only with spectrophotometer, where the detectors are strong and the low intensity light can be measured, not photometer, spectrophotometer, where the detectors are not sensitive enough to measure small intensity radiation. So this low volume cuvette probably cannot be used in spectrophotometers, but photofluorimeters, but spectrophlorimeters can very well use them as well. But we cannot use glass cuvettes, please remember here, because the excitation or emission, either both or at least one of them, happens in UV range, and the light, the glass is known to absorb UV radiation. That's why we cannot use glass as the material of construction. We only use quartz as the material of construction in case of cuvettes for fluorimeter. Now, the next part is detector. Detectors, there are three different types of detectors. Photometric detector, that's a barrier layer cell or photovoltaic cell, what we call, is generally is the most common and the most least expensive detector which can be used in fluorimeter. And this is how it works. It consists of a copper plate coated with a thin layer of cuprous oxide. A semi-transparent film of silver is coated on that, and then of course plastic case for the contact, for the non-conducting, to give the non-conducting surface. Now on this, okay, this can be silver or copper or anything, whatever you say, and the light falls on this through the window. This is the whole casing of the photovoltaic cell or barrier cell, and then it gets when the light falls on this oxide layer, which is there on metal oxide layer on the metal, the electrons are emitted from the oxide layer, move into the plate. That is the explanation is copper plate, but actually what is shown here is silver. So it passes to that silver layer, and then because the electrons are passed, the oxide layer becomes positively charged, metal layer becomes negatively charged, and that develops the charge, and this is connected to a galvanometer which measures the change, and that's oxide and the metal depends on the intensity of radiation. So the current measured in the galvanometer will be proportional to the amount of light which falls on the surface, and that is how the intensity is measured. Now the next one is photomultiplier tube. Photomultiplier tube works on a different principle. These are the commercially available photomultipliers tube. They don't look anything like this. This is only a functional diagram of photomultiplier tube. These are the actual pictures of photomultiplier tubes, which can be directly fitted in the instrument. And here you can see there are series of diodes. These are called diodes. Diodes are nothing but anodes. Okay, they are anodes, and this is a cathode. So the radiation which is coming from emitted radiation, which is falling, which is coming from the sample, passes through the cathode and falls one of these anodes. Right, it has a special material coated on the surface, and that multiplies the number of particles which are falling on this. Right, and then say if one particle falls, one light particle or photon falls, it is multiplied by it emits 4 or 5 photons, and those 5 photons would again fall on this second diode, which makes it 4 into 4, that is 16 diodes, and like this. And that is how the very low intensity radiation can be satisfactorily measured with photomultiplier tube, unlike photovoltaic tubes. All right, and there can be as high as 10 diodes are used. Generally, the voltage difference between two anodes is kept at 75 to 100 volts, so that the radiation would progressively move from anode 1 to anode 2, and they are not lost in transition. If there is no electrical difference, if they are not polarized by maintaining a potential difference, they may get lost, they may get scattered in the instrument during the process. So that is why it can detect the signals, very weak signals as well, and that is why it is very used to a very large extent in most of the instruments. Now, coming to the instruments, there are 3 types of instruments, and this is the single beam instrument, where we have only one source, and that source, the collimating lens and excitation and sample emitted and detected. Right, there's only one beam of radiation passing through the sample. That's why it's called a single beam radiation. There's nothing, a single beam spectrophotometer. This is what is usually available in most of the pharmacy colleges, because we don't do any high level work with the fluorimeter. We just generally do some quantification of drug substances in fluorimeter. That's why this single beam spectrophotometer is more, single beam photofluorimeter is more than enough. That's why this is what is available. Some instruments like ours may have double beam spectrophotometer. We have one of them, right? And that is very rare in the educational institutions, especially where BCom course is offered. The second one is called as double beam spectrophotometer. As the name suggests, double beam fluorimeter would have 2 beams. What are those 2 beams doing? One beam would pass through the sample and another would pass through the reference, that is the blank, either the solvent blank or the reagent blank, as I told earlier, so that the measured intensity of emitted radiation is only because of the sample and not because of the other constituents which are present in the sample. The diagram of a double beam fluorimeter would be something like this. You have lamp, and then on 2 sides of the lamp you have the reference solution and the standard, the sample solution. The emitted radiation from both of them would pass through, will emit, and then they pass through the excitation filter or secondary filters, and they are detected with the same photomultiplier tube alternatively, so that the difference between these 2 intensities is detected and recorded. Okay, now that is the best part of this. Now, spectrophotometer is generally the second, the double beam spectrophotometer. You don't have single beam spectrophotometer, fortunately. Single beam has only photometer, photofluorimeters. Single beams has spectrophotometer, double beams has spectrophotometers, where you use gratings or monochromators instead of filters. But otherwise it is same. You have the radiations passing through, and then the radiation is split in the monochromator itself into 2. One is passing through the sample and another through the reference. Now, what are the uses of a spectrophotometer? How do we, what is where is it used in analysis? It is used not only in pharmacy but many other applications. In pharmacy, there are good number of drugs which can be very specifically analyzed by fluorimetry. See, given the chance of any compound which emits fluorescence can also be estimated by UV visible spectrophotometer. Please remember. Okay. Now, if a compound can be analyzed by because there is absorption, right? Why it can be analyzed by UV is there is absorption. There is no emission without absorption. So absorption spectroscopy like UV can be used for all compounds which give fluorescence. But if a compound gives fluorescence, and we always prefer analyzing it fluorimetry than absorption spectroscopy, essentially because fluorimetry is more specific. Now, why fluorimetry is more specific? Fluorimetry is more specific only because it uses 2 filters. That means there are 2 specific wavelengths at which one compound can be detected. So even if the compounds have overlapping absorption maxima, they will have different emission maxima. And that is why the specificity of a fluorimeter is, fluorimetry as an analytical technique is always higher than that of absorption. Okay, so that is why if the compound gives fluorescence, natural fluorescence, then if that natural fluorescence is called as nascent fluorescence, so we always use fluorimetry than absorption spectrum. Now this is official in most of pharmacopoeia. There are a lot of pharmacopoeias which use this, and there are not many derivative fluorimetric techniques which are employed. It is simple, single point or calibration curve method which is used in fluorimetry. Even standard absorptive methods like as we discussed yesterday are not used in fluorimetry to a large extent. There are special applications here they are done. This can also be used as a detector in HPLC, and again, the specificity and the sensitivity is increased when fluorescence detectors are used with HPLC. Now the second application is analysis of environmental pollutants. Gases like nitrous oxide, nitrogen dioxide, etc. can be used, can be estimated in gas, in air, in atmospheric air by fluorimetry, and even sulfur dioxide can be estimated by fluorimetry in the atmosphere. And in the water pollutants, most of the most of the cations, the dangerous cations, heavy metals, etc., can be estimated by fluorimetry. Of course, they are not direct fluorimetric analysis. There are derivatization and complexation principles involved, which we will not discuss at this point of time. In medicine and biology, fluorimetry can also be used for the analysis of amino acids, and it is used for the analysis of proteins. Blood glucose can be very specifically and very sensitively estimated by fluorimetry. Serum chemistry, part of serum chemistry can be done. Creatinine is even now estimated by fluorimetry, and calcium ion both in water and in blood and any other body fluid, biological fluid, can be estimated. So this is one of the important analytical techniques. Pharmacy also, it has good applications, and this is what is all about the technique. Okay, now with this I would conclude and request madam to take over from here. This is a college, this is the university, this is the college where I'm working. We are one of the best pharmacy colleges in the country, NIRF rank 7, and then we are also QS ranking 200 to 250, world ranking, and this is what is the building looks like. Okay, with that I request madam to take over, go for questioning and the next procedure. Thank you all.
Thank you, sir. It was indeed a wonderful session, and you explained all the concepts very nicely. And especially you gave some real life examples for quenching. So I'm sure the students will never forget that quenching and all. So it was really a great session, sir. There are few questions. First question is, which method is more sensitive, UV or fluorimetry?
Okay, fluorimetry is more sensitive, essentially because it is always easy to measure weak radiation against a black background than weak radiation against a bright background. Like, all of we use night lamps. Now, these night lamps are very helpful in locating the switches at night. Whereas if the same night lamp is on during the daytime, we cannot even recognize that the lamp is on. Right? Many times it goes without our notice. That is because the light during daytime is so highly intense that the very weak light of the night lamps are not seen. Whereas in night, that is not the case. There are no background light. So those night lamps are the most useful only when in the absence of other light, right? In the absence of background light. So similarly, fluorescence is measured at 90 degrees to the light source. Now, light always travels in straight line. Because of this, the detector, which is kept at 90 degree, or of course, it is also kept at 37 degree in some instruments. Now, any which way, not at 180 degree in the light path of the source radiation. And that is why the detector in case of fluorimeter is in dark. And that is why it can sense the emitted radiation to a higher precision than the light kept at 180 degrees. And that's why it is more sensitive as well.
Okay,
Yes, ma'am.
thank you. There is one more question, sir. Why phosphorescence measurements are done at low temperatures?
Because phosphorescence is only seen in low temperatures. At room temperature or higher temperature, we generally don't see phosphorescence. They are not in a measurable condition.
Okay, thank you, sir, for the answer. And sir, one more question that nowadays double beam spectrometers are available and their
Right.
advantages in single beam. So are actually single beam spectrometers for any instrument are used nowadays as such?
UV visible spectrophotometer or spectrophlorimeter you are talking about?
Sir, for a spectrophlorimeter as well as a UV visible spectrometer.
Spectrophlorimeter, most of the pharmacy colleges, what I have seen, have single beam only. There are very few double beam spectrophlorimeters in at least pharmacy colleges.
Yeah, but in industry.
Yeah, good.
In industries, which they prefer. So single
Industry
beam or
depends on the application. Go ahead, madam. Yeah, you were adding something to the question. Go ahead.
yes, sir, same. I mean in industries which are preferred. Single beam or double beam.
Industry depends on the application. If the official assays are done, then double beam is preferred. But if it is for some other, add-on test in the monograph, rarely used, then single beam also is fair enough, and industry also uses single beam. Because see, double beam comes, it's not only the investment which is expensive, calibration of double beam spectrophotometer is also expensive. The maintenance of double beam spectrophotometers are fluorimeters are expensive. So if the outcome of those instruments does not justify that expense, industry is not going to use it. So if the industry say, for example, a bulk drug unit which is manufacturing thiamine hydrochloride, they would obviously have a double beam spectrophlorimeter because thiamine is officially assayed using spectrophlorimeter. Whereas a manufacturer who is doing, say, ibuprofen and paracetamol tablets may not really have a double beam spectrophotometer, because once in a while, maybe to test, perform some small test of the monograph, they will need a fluorimeter. They manage with single.
Okay. Thank you very much, sir. Sir, one last question, that
Go ahead.
how the density of solution affects fluorescence.
Sorry.
How the density of solution affects fluorescence.
Density does not, viscosity does.
Okay.
Higher the viscosity, higher is the intensity of radiation. Emitted radiation. Emitted radiation.
Okay. Thank you, sir, for answering all the questions. I would now request my colleague Pooja Magar to take charge of the session in present vote of thanks. Pooja, madam.
Yes. Am I audible?
Yes, madam.
You are audible.
Okay. Okay. Now we are heading towards end of the session. So let me grab the opportunity to propose vote of thanks. It was indeed privilege to have Dr. Krishnamurthy Bhatt for his insightful lecture on UV visible spectroscopy and spectropolarimetry, theory and instrumentation part. This session was divided into two sections, which have covered the crucial aspects of UV visible spectroscopy and spectropolarimetry. The staff and students who are attending this lecture may have got extensive perception of both UV visible spectroscopy and spectropolarimetry. It will be definitely go in long way in their curriculum. Thank you, sir, for sparing your precious time with us. I also extend my sincere thanks to our management, trustee, honorable president, for providing such a great platform and constantly boosting us to achieve new heights. I would also like to thank our principal, Dr. K.H. Jain sir, for constant motivation and enthusiastic contribution for successful conduction of the event. I also forward my sincere thanks towards our DPharm principal Hirode sir for his valuable guidance and support. I express my gratitude towards all dignitaries from various institutes for their presence. I forward my gratitude to all technical committee who is standing firmly for successful execution of this webinar. Finally, yet importantly, I thank you all teaching and non-teaching staff for their continuous support and to all attendees for their great response. Thank you. Now I'm requesting Dr. Jain sir to allow me to conclude the session. Please, sir.
Before concluding the session, thank you very much. I profusely thank Krishnamurthy Saab for continuously guiding the people for last 2 days. And
It's my pleasure, sir.
I welcome Dr. Redasmi, who has been there. He's our Deputy Dean of Pharmacy and who has been there for continuously. Yesterday also he was there and today also he is there. And being a chemistry person, he is sitting sincerely. I had a discussion in between. I had a small break in the internet connectivity, but I have come back. And it is indeed, this will definitely go on record. Yesterday's session was also good. We have already sent you the recording, Dr. Krishnamurthy, of yesterday's session, and today's also we will send. And your very special knowledge, it was too deep sometimes to understand for the students, but the people like us have got some insight about the subject. Some lacunae were there in our knowledge, because I only know how practically you have been involved in working since Ahmedabad and Manipal, and so thank you very much. I thank everybody, one and all the attendees, and also both the organizer team and the technical support. All the trio has worked hard, and finally a good session has come to end. To a certain extent it may definitely help to the students, and our little bit of endeavor may be fulfilled. Once again, thank you very much, Dr. Krishnamurthy, and Pooja madam, you can close the session.
Yes,
Thank
yes, sir. For participants, feedback link is provided in chat box. So you have to fill the feedback form and you will get e-certificate. Thank you so much again for attending the session. Now with the due permission of our speaker and principal sir, I hereby declare that webinar is over. Stay safe, stay
And
healthy.
will you share the feedback with me also? Please share.
Yes, sir. Yes, sir.
Yeah.
I will share.
Yeah,
Okay,
yeah,
sir.
we will share that. Today you can see on the WhatsApp, I have sent you the YouTube link of yesterday's session. You can enjoy it.
Oh,
And
okay.
yeah, I sent you. 1 hour back I sent you. You were involved in you have just started your lecture. And
Okay.
tomorrow we will send this also.
Yes.
Yes,
Yeah.
sir. Yes,
Thank you.
sir.
And I will request madam to send you the feedback also.
Yes, sir. Yes, sir.
Okay.
Okay.
Thank you, sir.
Thank you so much, sir.
Thank you. Thank you.